Welcome back to ECE 501B. You have one more homework assignment due before Exam 2, and some of the material that we are presenting may not be on Exam 2. It's only up through homework 6 that will be exam number 2 is what I'm planning. So it's whatever homeworks we've had. I think it's 4, 5, and 6. Those will be the homework topics that will be addressed on exam number 2. And with the third edition of the book, some of this material that we're talking about today from the second edition, 6th chapter, is actually in the in chapter 7 of the third edition. When we start talking about adjoint, that's actually in chapter 7 of the third edition of the textbook. In the second edition, it's in the 6th edition, and my numbering is based on the second edition of the textbook. Hopefully that won't throw you off. Just as a reminder, the project is due on our last day of class. I believe that's the 9th. I hope that's the correct date. That's when I wanted it to be. And there is material on Exam 2 and the project on D2L, and the project will probably refer you, or it does refer you back to the course resources module on the D2L website, which is on the content page. What I want to do today is recap what we've talked about relative to linear functionals, and that is a map, a linear map from some vector space into the scalars. And we showed last time via a prop or a theorem that you could actually parameterize or capture that linear functional in the form of an inner product. And that's what I'm meaning in parentheses here. This linear functional applied to U is equivalent to that whatever arbitrary vector U to some unique vector W. Then we will again recap what we had quickly defined to be the adjoint, and we'll walk through a quick example there. And we will then start going through some of the properties of the adjoint, showing that it's linear, which really are the same two properties that we've used for this linear map, additivity and homogeneity. We will talk about these relationships, or that there are in fact relationships between range space and null space for these two different maps, the linear map T and the linear map T's adjoint, or T dagger. And there is a relationship between range space, null space, and orthogonal complements to those appropriate spaces, and we'll look at that. Then we will see that the matrix representation for the adjoint is actually, if we have a matrix representation of the linear map T, and we call that A, we will see that the adjoint is the complex conjugate transpose in terms of the matrix representation of the adjoint T. And then in the second edition, we get into chapter 7 and start talking about operators on inner product spaces. And when we start saying a self-adjoint operator, that means that the operator T is equal to its adjoint. And that will, I hope, make a little bit more sense after today's class. To recap what we had talked about last time, here is that theorem, 645, that I had referred to, relative to a linear functional. A linear functional really is a linear map T that goes from some vector space V into the scalars, where that scalars could be either the reals or complex numbers. I'm just referring to it as F. It's a linear map, which means it satisfies additivity and homogeneity. And Theorem 645 says that if you're given a linear functional on this vector space V, then you can actually find a unique vector W, which when used in an inner product on that vector space V, you can make that equal to this linear functional phi. Our inner product takes two vectors from our vector space and generates a scalar. And we can find the unique W here is the formula to find that unique W. You first need an orthonormal basis for your vector space V. Once you have an orthonormal basis, then you apply this linear functional to each one of those basis vectors, E1 through E sub n, conjugate that, and that's going to be a scalar conjugated. And those scalars then weight the appropriate or their corresponding orthonormal vector E1, E2 up to E sub n. And that's we showed via a proof where that came from and how we could then determine or say that this boxed formula is in fact the formula to create this unique vector W. And if it's a unique vector W, one of the interesting properties is it really doesn't matter what you start out with for your orthonormal basis on V. We could have two different orthonormal bases on a vector space V, and they both, if you follow this formula, will give you the unique W that this particular theorem is claiming. And we showed last time that indeed it was a unique vector W. Then we talked about very quickly this notion of an adjoint. If we're given a linear map T from a vector space V to another vector space W, and this is actually these vector spaces V and W both need to have inner products on them, so they're both now inner product spaces, V and W, and they don't have to be the same vector space. You now have a linear map from V to W. The adjoint goes in the other direction. It goes from the inner product space W back to V. And it does so in such a way that the inner products that are shown in blue are equal. If we now have a vector V, little vector V, we operate on that with the linear map T. TV actually lives in W, the vector space W, as does W. That's now using the inner product space on W, and that's equal to the inner product generated by V T dagger W, that's the inner product of or on this vector space V. The idea behind the adjoint is what do we need to do to this linear map T so that we can actually slide that same or a consistent linear map to this other slot in an inner product and have those be equal in terms of the resulting inner product. That's one way of thinking about this adjoint. How can we sort of move that linear operator to the other slot? And that means that it becomes an adjoint, but that's really sort of one way of thinking about the adjoint as a concept. How do you make that happen? Or how do you define T dagger so that this equality of inner products is the same or exists? So let's now look at building or creating an adjoint, and let's do it so that V and W are different. Here V is R3 and W is R2. So this is a dimension reducing linear map T, and suppose that we just say that this linear map T, taking the three coordinates x1, x2, and x sub 3, let's say the linear map goes or produces a first coordinate in R2 of x2 plus 3 x sub 3, and suppose the second coordinate scales the first coordinate by 2. And that's now our linear map. We want to now find the adjoint of that linear map T. What can you tell me right away about T dagger as a linear map? it now goes from W to V, and what was W? What was that inner product space? Now we're going from a two-dimensional vector to a three-dimensional vector. And we want to now find that mapping from 2 to 3 such that the inner products of TV, comma, W is equal to V, comma, T dagger W. We know how big T dagger is, or what it looks like in terms of a linear map. We now need to find that relationship. As an exercise, let's say to create T dagger, let's just pick a vector W that's in R2 in W, and let's just go ahead and parameterize the coordinates of that particular R2 vector. Let's call those, obviously enough, Y1 and Y2 for W. But at least this now allows us to talk about the first coordinate or component of the vector W and the second component of the vector W. We now need to make sure that we can select T dagger, or how does T dagger map Y1 and Y2 into R3? That's what we're asking, and we want that to happen in a way that V, T dagger W, must equal TV operating, or inner product with W. That's just the definition. Of the adjoint. And what we're going to do is sort of work our way through this and then start equating coordinate or components in these inner products. So let's now say that we have a V, comma, T dagger W, so that now we have V, which was this 3 vector, inner product with T dagger W, but W was Y1, Y2. And by the definition of the adjoint from up above, this is just our vector V, and this is our vector W. That's V, comma, T dagger W. We know that that's equal to TV, which is T operating on X1, X2, X3, with W, which is Y1, Y2. And that equality is just the definition of the adjoint. Now let's go ahead and apply that linear map T on X1, X2, and X3, and that said that that now maps to this 2 vector, X2 plus 3X3, comma 2X1. Or we now have X2 plus 3X sub 3, comma 2X1. That's the result of the linear map T. And that's now going to be inner product with Y1, Y2. If we apply the Euclidean inner product, we now just multiply, and this is in R2, we don't have to conjugate anything. We just multiply the coordinates and add up this product of those coordinates, meaning we have X sub 2 plus 3X sub 3, the first coordinate in the first slot times the first coordinate in the second slot, plus 2X sub 1 times y sub 2. Or if we push that all the way through, we have x sub 2 y1 plus 3x sub 3 y1 plus 2x1 y2. That's now T, V, comma, W. We know, though, that that's equal to, or should equal, V, comma, T dagger, W. Which line? The first black line. So what's the first black line? What did I do there? What did I... So how did I get 2x1 times y sub 2? Where did that come from? That's just the standard inner product. So now I'm multiplying consistent coordinates in the two vectors. I have coordinate 1 in slot 1 and coordinate 1 in slot 2. I multiply those. That's where the y1 times x2 plus 3x3 comes from. And then I have 2x1, the second coordinate in the first slot, times the second coordinate in the second slot, which is y2. Is that? Then I simply distributed those variables, and I ended up with a string of 3 products. And what I want to do now is basically make that equal what I've now written in blue. And what have I written in blue? Well, I now know that in blue, this is supposed to be equal to this guy. And if I were to take x1, comma, x2, x3, that's V. If I start to identify these components in the last black line relative to x1. So now I have 2x1, y2. I'm just going to reorder those so it looks more like x1, x2, x3, plus x sub 2, y1, plus 3x sub 3, y1. And what I'm trying to say is if I identify the components in V, x1, x2, and x3, and if I remember that that's a standard inner product form, then whatever I'm multiplying by x sub 1, that must be in the first coordinate of T dagger W. So this is now supposed to equal x1, x sub 2, x sub 3 times something, and that something is now what multiplied x sub 1? 2 y sub 2. That's the first coordinate in my T dagger W result. T dagger W needs to be a 3 vector. It's taking a 2 vector W into a 3 vector. Now I've said, oh, what in this result is scaled by x1? It's simply 2y sub 2. What in that line near the bottom is scaling x sub 2? Well, that's just y sub 1. And what scales x sub 3 is 3 y sub 1, and that's actually what needs to be. If I associate that with the corresponding location in that final inner product, this must be T dagger W, which W was parameterized as y1, y2. Or, now we know what the linear map T dagger does to y1, y2. That simply takes y1, y2, and it populates a 3 vector, and it does that in the manner of saying, oh, take the second coordinate and scale it by 2, and that will become the first coordinate in T dagger W. The second coordinate is just the first coordinate of the original, and the third coordinate is 3 times the first coordinate. And that's now the linear map T dagger corresponding to the linear map T that went from R3 to R2. And we did it by really just enforcing this relationship of equality between the two inner products. And that's what we ended up with. We knew that T dagger needed to go from R2 to R3. R2 is W, and now that maps into V, and V was in R3. And this is now our 3 vector. Are there questions on that example? That was supposed to be a quick example. We'll look at more interesting examples in a little bit, but I hope this gives you a feel for what this adjoint might look like. It's really just another linear map, but it's now mapping from W to V. Let's look at some of the properties. Of this adjoint. And one of the questions you might ask, although I've already said it's linear through that whole example, but is T dagger a linear map? And if it is linear, if it is a linear map, what properties does a linear map possess? Homogeneity and additivity. We need to then show that T dagger does possess additivity and homogeneity properties. If we look at additivity, then we have TV with W1 plus W2, and that's maybe why we call W having coordinates Y1 and Y2. Now W1 is a vector and W2 is a vector. What do we know about the second slot and an inner product in terms of additivity? Do we have it, or do we have to do something different? No, we have it. So we can just write this as a sum of 2 inner products because of additivity of the second slot. We can write this as TV, comma W1 plus TV, comma W2. But by the definition of the adjoint, what is TV W1? Now we want to slide that operator into the second slot so that now we have V, comma, T dagger W1 plus V, comma, T dagger W2. But if we applied the adjoint formula to the original left-hand side, what would that look like? What's the left-hand side equal to if we used our adjoint relationship? Now we're moving that T to the second slot. We end up with V in the first slot, and then we have T dagger operating on W1 plus W2. And now if we simply equate, well, what I failed to do, oh, you're going to not like this, but I can add space. I skipped a step. So I can cut my paper and add in some more, sorry. But this is, we can now do the additivity of the second slot, and we can say V comma T dagger W1 plus T dagger W2. And now you can, I hope, see that if we equate the second slot in those two formulas, we do have additivity of the adjoint. This now says that T dagger W1 plus W2 is in fact equal to T dagger W1 plus T dagger W2. We've justified additivity, or we've shown that additivity is true on this adjoint. If we look at homogeneity, doing that in a similar manner, then we would say, oh, TV inner product with a scalar A times W. What happens to that scalar in the second slot if we move it outside the inner product? That's the conjugate homogeneity property. That now says that we have A conjugate TV comma W. Now if we apply our adjoint relationship on that inner product expression, I'm not touching the conjugate of A, but now I'm simply using the definition of the adjoint, and I say, oh, if I slide that T to the second slot, I have V T dagger W. But now let me put that scalar back into the second slot. So that now that needs to be the conjugate of that scalar in the second slot. I now have V comma A T dagger W. But what do we know the left-hand side of this original top line must equal if we apply our definition of the adjoint? Applying the definition of the adjoint and moving that T to the second slot, we now have T dagger applied to the vector W that's scaled by A. And now if I equate these two second slots in my inner product, I can now say that, in fact, T dagger operating on a scaled W, where the scalar is A, is equivalent to or equal to A T dagger W. And now I've just demonstrated homogeneity. Consequently, T dagger is a linear map, and in general, if we have a generic linear map, then it's not necessarily an operator. We're taking this linear map between two vector spaces, V and W. If T is a linear map from V to W, then T dagger is a linear map between what vector spaces or inner product spaces. That now takes W to V. The adjoint also enjoys some other properties. Let's just write those down. One is additivity. If I had two maps, linear maps S and T, and I added those and then took the adjoint, that's equivalent to taking the sum of the adjoint of S and the adjoint of T individually. I also have the property of conjugate homogeneity. Which means that if I now scale the linear map T and find its adjoint, that's equal to the complex conjugate of that scalar applied to the adjoint T. What do you think happens if I now take the adjoint of an adjoint? Meaning, I'm now taking the adjoint and taking its adjoint. So the adjoint goes from W to V. The adjoint of the adjoint must go from V to W, and in fact, it goes there according to the original linear map T. Which means if you're playing around on Friday night and you start taking the adjoint of all these linear maps, you keep repeating and eventually you get back to where you started. I'm sure you're all going to do that. We also have the identity and its adjoint. What happens when we take the adjoint of the identity map? It's the identity map, so it's self-adjoint. Pardon? So now if we have the identity map I, what does that tell us about V and W? So now they're the same, aren't they? And if they're the same, then the identity or the adjoint of the identity makes sense that it's the identity. One more, and that's dealing with the products of maps. Suppose that I now, or the composition, however you want to think of this, what if I take the linear map T and then map that, or take the result of that and apply the linear map S, and now take the adjoint of that? This is similar to what happens when you take the transpose of matrices or take the inverse of matrices. You have to reverse the order of these so that now you have T dagger, S dagger. And that's true for all T. Let's say T goes from V to W and S goes from W to U. Those are some properties of the adjoint. Let's now look at this relationship between null space and range space of the different maps and their adjoints. Maybe that word interesting is subjective, but let's say useful. Or maybe there is an interesting, since I use is, let me just say relationship between these spaces, these null and range spaces of T and T dagger. And the book in the second edition has these as Proposition 46 in Chapter 6. And that says if we have a linear map T mapping between V and W, then we can have four different relationships. We can say that the null space of the adjoint of T is equal to not the range of T, but its orthogonal complement. So the perp of the range of T. If we wanted to know something about the range of T dagger, we could find that same space by subspace by looking at the null space of T's orthogonal complement. And we have similar relationships if we start with the original linear map. The null space of T is equal to the range space of T daggers, or the orthogonal complement of the range space of T dagger. And finally, for the range of the linear map T is the same as the orthogonal complement of the null space of T dagger. If you look at these a little bit, do you see that 1 and 4 are related by taking the orthogonal complement of both sides? If you took the orthogonal complement of 1, you would end up with 4. And if you take the orthogonal complement of, let's say, 2, you get back 3. So really we just need to look at 2 of these, and the others we can just take the orthogonal complement and we'll have all 4 demonstrated. Let's look at the first one. For I. Let's just select a vector W that lives in the null space of T dagger. That's the first subspace in I. So now we're just generically selecting a W in a vector W in the null space of T dagger. What does that mean about T dagger and W? If I operated on that W with T dagger, what would I end up with? If W is selected to be in the null space of T dagger, what's T dagger W? That's the 0 vector. Now let's just look at the 0 vector. What vectors are orthogonal to the 0 vector? All vectors. So let's just say you'll buy that, won't you? V comma 0 is the 0, is a scalar 0. But we just said that the 0 vector can be found by taking or operating on W with T dagger. So let's just say this now says that if we had V and we inner product that with T dagger W, that's going to give us Z. 0, the scalar, for all V in the vector space V. So if you saw this maybe in a math book or in our book, maybe they just give you the second part of this. Maybe they don't tell you this 0 is equal to V comma 0 vector inner product. What's the definition of the adjoint? If we apply that to this most recent expression on the last line, now we're moving T dagger into the first slot, and what will that result in? And that's now equal to 0, and that's true for all V in the vector space V. But what does that say about this vector W that we arbitrarily selected from the null space of T dagger? Where does W live? Or what does TV give us? If we take any V and operate on it with the linear map T, where are we going to end up? The range of T. Now we're saying that W is orthogonal to the range of T, because this inner product is 0. We're saying now that this last expression, this inner product equaling 0, is really saying that W is an element of the orthogonal complement of the range of T. But we arbitrarily picked W to be in the null of T dagger. We didn't have to make any special arrangements with W. It was all W in the null of T dagger. That then says that all of the null of T dagger is equal to the range of T's orthogonal complement. And that's the first statement in that proposition. We needed to show that the null space of T dagger was the orthogonal complement or equal to the orthogonal complement of the range of T. Now let's do something similar to 3. Because we know 1 and 4 are similar, we just have to take the orthogonal complement of one and get the other. Now 2 and 3 are similar. Let's start with 3 and say let's pick V to be in the null space of T. Then we know that TV is equal to 0. And we can do this a similar approach or process to demonstrate what we need to demonstrate. We know that the 0 vector is orthogonal to all vectors, and now we want to use the particular 0 vector of TV, where V is any vector in the null space of T, so that we now have TV inner product with W is equal to 0 for all W, and our definition of the adjoint now allows us to slide that linear operator t to the second slot by saying now v comma t dagger w is equivalent to what it was above, and that was equal to 0 for all w. And now that says that v is in the orthogonal, or is orthogonal to the range of t dagger. But v started out being in the null space of t, and we've now then shown the equivalence of the null space of t and the orthogonal complement of the range of t dagger. There's 3. 3 was equivalent to 2 if we take orthogonal complements, and 1 was equivalent to 4. I'm just going to make that statement then. Taking orthogonal complements of both sides of 2 and 4 of remaining entries brings us back to what we just demonstrated, and that then would allow us to complete the proof of that proposition. Now we have some relationship between T and T dagger in terms of range space and null space. Let's look at what these linear maps, T and T dagger, might look like in a matrix representation. Or there's a useful relationship between the matrix representation of a map and the matrix representation of its adjoint. Which is proposition 47 in chapter 6 of the second edition. Suppose that we now have a basis, and it's an orthonormal basis, and I'm just going to say that's this list A. A is a list now. A is a list of orthonormal bases. If A is, whoa, good, I'm saying an. If A is an, maybe I should somehow make that stand out. I'll put it in quotes. If A is an orthonormal basis on the vector space V, and B is similarly an orthonormal basis on W, then the matrix representation of T dagger, comma B A, B and A, B is the orthonormal basis on W, A is the orthonormal basis on V, that matrix representation of T dagger is the conjugate transpose of the matrix representation of T, comma A, B. I'll send you to the book for that proof. Let's just remind ourselves of what we mean by the conjugate transpose of a matrix. If I give you, and I'll make it non-square just to emphasize the transpose characteristic, suppose we have a 2 by 3 matrix, A, B, C. I'm going to get really creative with the elements in that matrix. There's our matrix. It's 2 by 3, A, B, C in the top row, D, E, F in the second row. The conjugate transpose of that matrix is A, B, C, D, E, F, conjugate transpose. Now the first row becomes the first column with all of the elements conjugated, where I now have in the first column A, B, C, and those are all complex conjugates, and the second column is D, E, F, conjugated. Which means if you have the matrix representation of a linear map, then you can transpose that matrix representation and then take the complex conjugate of all the entries. Or you could do the opposite. You could complex conjugate all the entries and then transpose. Let's look at an example. So Hermitian is, the question was, is that Hermitian? It's not unless you're setting it equal to something. So a Hermitian matrix really means that it's self-adjoint, which means the matrix is equal to its complex conjugate transpose. So if I just say, take the complex conjugate transpose of a matrix, I'm not saying that it has to equal anything. I'm just having you do that as an operation. But the Hermitian of a matrix T would be equal to its complex conjugate transpose. If a matrix was Hermitian, then if you took the complex conjugate of that matrix, it would be equal to the original matrix, if it was a Hermitian matrix. Does that make sense? So if I just take the complex conjugate transpose of a matrix, I'm not saying anything about whether that matrix is Hermitian or not. This matrix here, this example, is A, B, C, D, E, F Hermitian? No, it's not square. Hermitian would at least have to be square in order to equal itself, and if you took the complex conjugate transpose, it would have to be the same. We're getting a little bit ahead of ourselves, but that's a good question. You maybe heard the Hermitian. Now, when I start talking about self-adjoint operators, you can think Hermitian. I'll say, here's a self-adjoint operator, and you'll go, Hermitian. It's the same. Okay? Let's look at an adjoint example. Since I'm labeling it 1, you know I have more than that. Here's the first one. Suppose that I'm taking a linear map T between C3 and C3 in such a way that suppose that I have the linear map operating on this 3 vector x, y, z, and that produces now in the first coordinate it takes 2 of the 2x plus 1 minus I, y. That's the first coordinate. The second coordinate is the complex number 3 plus 2i, or complex scalar, times x, minus 4iz. That's the second coordinate. I need to map to 3 coordinates since I'm going from C3 to C3. And the final third coordinate is 2i scaling x plus the complex number 4 minus 3i times y minus 3z. And now I want you to find the adjoint of that linear map. One way to do it would be to find the matrix representation of this linear map T, then take that matrix representation's complex conjugate transpose, and then take that matrix back into this linear map notation, and that linear map notation would be T dagger. Let's try that. What's the matrix? So here's our attempt at a solution. What's the matrix representation of T, and I'm going to call it A. And unfortunately, my screen's not big enough. But this matrix representation takes 2 times the first coordinate, and so the first row of this matrix representation of A needs to produce this first coordinate when it is operating on a vector x, y, z. So that now this A matrix better be a 3 by 3 matrix. In the 1-1 entry of that A, it's going to be 2 that scales x. Then what scales y? To give me my first coordinate, that's this 1 minus I. And what scales z? Nothing, so 0. Is it clear where that's coming from? That produces now my first coordinate in the result of applying that linear map. The second coordinate needs to scale x with the complex number 3 plus 2i. It's not scaling any y. I put a 0 in there, and then it scales z with minus 4i. And finally, then the third coordinate is 2i times x plus 4 minus 3i times y minus 3 times z. Now, if we want the matrix representation of T dagger, that's the complex conjugate transpose of A. What happens along the diagonal? I just have to conjugate that, don't I? And they're all real, so those are going to stay the same. I can just say 2, 0, and minus 3. I've done the hard part. What's in the 1, 2 entry of A star transpose? Okay, it'll be the conjugate of the 2, 1 entry of A. The 2, 1 entry of A is 3 plus 2i. We conjugate that and we end up with 3 minus 2i. What's going to be in the 3, 1 entry of A star transpose? The lower left corner. Lower left corner, am I not? So now I want down here, I'm pointing to the lower left corner on the screen. I'm sure everybody watching the video saw that. But this is now going to be 0. And now if I map that 2i's conjugate up to the 1, 3 entry, that's minus 2i. I'm basically just flipping things across the diagonal now. And this now becomes 4i, and I have 4 plus 3i, and finally my 2, 1 entry in A star transpose becomes 1 plus I. Now I'm suggesting that that implies what T dagger is. T dagger operating on X, Y, Z is just translating this matrix back into the linear operator structure. What scales X in the first coordinate? 2. Then I add to that 3 minus 2i times y minus 2i times z. Is that right? There's my first coordinate. Then the second coordinate will just be 1 plus I times x plus 4 plus 3i times z. And finally, I have 4i times y minus 3z, and that's now my adjoint map for the linear operator T. What if I now look at another, maybe an easier example? Maybe we started with the hard one. I didn't hear any rumbling, so I'm assuming we were okay on that first example. Suppose now that T is in R3. And it maps, so it's a linear map from R3 to R3. Suppose that T of X, Y, Z now becomes, first coordinate is 2x plus y, second coordinate is 3x, and the third coordinate is 4y minus 3z. I'm hoping now you can really just write down that matrix representation without a whole lot of effort. The first row in A is, what do I have to populate the first row to produce 2x plus y if this A is scaling x, y, z? 2, 1, 0 is my first row. Second row, 3, 0, 0, and the third row. Now I need to take the complex conjugate transpose of that, or I could say A dagger if I wanted to maybe use a new notation. I can conjugate those pretty easily. They stay the same. Now I simply reflect across the diagonal. My diagonal stays the same. That's 2, 0, minus 3 down the diagonal. I have 3, 0, and to complete the first row. The second row is 1, 0, 4, and the bottom row is 0, 0, minus 3. So that now I can produce the adjoint of my linear map T, and that becomes 2x plus 3y in the first coordinate, x plus 4z in the second coordinate, and minus 3z in the third coordinate. Now, as a check on our work, we could actually do what? Could we perform sort of a quick check to see if we're in the right ballpark, since we're dealing with ballparks at this point in the year, World Series? Maybe. Oh. So let's look at a particular example with this T and T dagger that we just created. So now we have this T going from, let's say, V to W. What if I simply selected two vectors, one in capital V? I know it has to be a 3 vector. And what if I picked a vector in W for this T that I was working on? It too is a 3 vector. Now, what if I form the inner product of TV with W? T was 2, 1, 0, 3, 0, 0, and 0, 4, minus 3. And V was 1, 1, 0. Do you remember how we can quickly multiply these? What am I doing? I'm just adding the first two columns together, so that now I have 3, 3, 4. And I now want to take that, TV, inner product with W, or I'm now taking 3, 3, 4 and inner product, forming the inner product of that with 0, 1, 1. I now simply multiply compatible coordinates and add up their product. I have 3 times 0 plus 3 plus 4, or that's 7. All right, I generated a number. What good is that? If I'm supposed to be checking my work, what should that equal? That better equal V, comma, T dagger W. If we now look at that, we have T dagger W. T dagger was 2, 3, 0, 1, 0, 4, 0, 0, minus 3. W was 0, 1, 1. And now I'm simply adding the last two columns. And that's 3, 4, minus 3. Which, if I now take the inner product of V with T dagger W, V was 1, 1, 0, T dagger W, 3, 4, minus 3, and I now have 3 plus 4 plus 0, or 7, and at least I have a little bit of a sanity check on my work, maybe, that way. Questions on that? That's supposed to be true for any V and any W. We just picked two out of the hat and verified that indeed TV comma W inner product was equal to the inner product of V comma T dagger W. That's now Chapter 6 of the second edition. Let's move into Chapter 7, which we've already been there since we've been starting to talk about adjoints if we were looking at the third edition of the textbook. Chapter 7 is dealing with operators, and now we know what operators are, and we know what inner product spaces are. And let's then talk about this special notion of, now that we have adjoints, which don't have to be an operator, let's make them an operator and see what it means for that operator to be self, adjoint. In this case, an operator T, since it's an operator, it's mapping V back into itself and it's linear. Is self-adjoint, or as we tried to talk about just a minute ago, you can also say it's Hermitian if the linear map T is in fact equal to its adjoint. Now, did this T dagger, I don't know if we can see all of these together, where is that matrix A, according, or that's the matrix representation of T, is it self-adjoint? It's real, so we don't even have to worry about the conjugate, do we? But we would need it to be equal to its transpose, and it's not, is it? A and A dagger are not equal. So that's not a self-adjoint linear map. There's an example that's not, it is an operator. It goes from R3 to R3, but it's not self-adjoint. Obviously, then, this is imposing certain constraints on this linear map. What do we know if we have a self-adjoint operator? What kind of constraints does that impose on this matrix representation of that operator? What do we know the matrix must be in terms of its shape? Needs to be square. Why does it need to be square? The obvious reason is operators have to be squared, and we're saying it's a self-adjoint operator, so there's one. One justification, so that T is taking V to V. And B, if we looked at the matrix representation of T, if it was, let's say, on the field F and it was N by M, then that would not equal the matrix representation of T dagger, which would be on over the field of numbers M by M. And these are then different shapes. When N and M are different. If we now have a matrix representation of this linear map T, let's say that it's 3 by 3 and it's A, B, C, D, E, F, G, H, I, then what does the matrix representation of T dagger look like? Let's not say anything about, right now, it being self-adjoint. What would we do, or what would we end up with if we looked at the matrix representation of the adjoint of T? How would we find that? We could conjugate all of those entries and transpose it so that I now have A, B, C, D, E, F, G, H, I, all of those conjugated. Those are some pretty bad conjugates. But now I want you to sort of look at that after you take the transpose and say, when would that matrix representation on the bottom be the same as the matrix representation up top? That's what would be required for that matrix or that linear map to be self-adjoint. So we'll pick up at that point on Monday.